Hi all, this is a previous year DOM question. We have shaft which is subject to bending load, axial load and torsion load. You can see from the figure that the axial load is 25 kilonewton. Bending load, I mean the force that causes bending is 5 kilonewton, and their torsion load of the 1500 newton meter is also applied. Total length of the given bar is 450 mm, and the diameter of the. Hi all, this is a previous year DOM question. We have shaft which is subject to bending load, axial load and torsion load. You can see from the figure that the axial load is 25 kilonewton. Bending load, I mean the force that causes bending is 5 kilonewton, and their torsion load of the 1500 newton meter is also applied. Total length of the given bar is 450 mm, and the diameter of the bar is 60 mm. We have to calculate the diameter is given as 60 mm. So we have to find the stresses at the A and B. That means top and bottom portion of this uh, shaft. So let's look at the detailed solution. So this is the solution of this given problem. I have drawn the given figure, and first of all we have to write the given condition. Length of the shaft is given as 450 mm. I'm assuming the axial load to be as F1 and the bending load as F2. Okay, you can use any letter. Okay, I'm assuming the axial load to be F1 and bending load is F2. So F1 is given as 25 kilonewton. You can see from the given figure, and F2 bending load is given as 5 kilonewton. And small d is the diameter of the shaft, 60 mm, and torsion load is 1500 newton meter. Okay, we have to convert all this into Newton mm. So this kilonewton, I haven't written it, but this kilonewton have to convert it into Newton, because we need to get the stresses in megapascal. For that it has to be Newton and mm, all the units. So here the torsion load is given in 1500 Newton m meter. So that meter has to be converted into mm. That's why it is multiplied by 1000. So it is 1500 into 10 raised to 3 Newton mm. Okay. So the very first step when solving this type of problem is identify what type of stresses are there. We have axial load, bending load, and torsion load. That means we need to find axial stress, bending stress, and shear stress. Suppose in this question there was no torsion load, just simply the bending load and axial load. Then we need to only find the axial stress and bending stress. Since we have torsion load, we need to find shear stress also, because this torsion load will create a shear stress. We all know that, right? So similarly, bending load will create a bending stress, and axial load will create a axial stress. So we have to find all the three corresponding stress. So axial stress is simple equation of axial is axial force or axial stress is F by A. Okay, since I have named it as F1, I have written it as F1 by A. So F1 that's 25 kilonewton has to be converted into Newton. So multiplied by 1000. Then area, it is having circular cross section, it will be cylinder. You take the cross section, it will be circular in shape. So area will be the area of circle. That means pi d by square by d square by 4. So simple substitution, we get axial stress as 8.84 megapascal. Similarly, bending stress is m by z. Is the formula. The result is a section modulus, which is a pi dq by 32. Okay, that's 32 at the denominator has gone up, and m means moment. So moment is simply force into distance. How does this moment occur? This moment is caused due to this bending force 5 kilonewton into this distance, right? Whole distance. So that will create a moment. So that's this m is actually f2 into l. Right, this F2 force is what causing the momentum, and this Z is pi dq by 32. This 32 was supposed to be in the denominator. Okay, when denominator will go to numerator. We know. So this rearranged into this equation. In this equation, we know all the value. Just simple substitution. Here also the force has to be converted into Newton. So multiplied by 1000. So the bending stress is 106.1 megapascal. Same way, shear stress has to be found by using this equation. You don't need to learn any of this equation. These all equation are in the data book. So here 16 T by pi d cube is a shear stress. The torsion load is torque is given in the question. It has to be converted into Newton m, which I already done in the previous step. And D we know value. So shear stress value is 35.36 megapascal. This is a very first step we have to. Okay, this is the first step. Second is to find the resultant stress at this A and B. Okay, resultant stress. So when we taking resultant stress, we won't be considering the torsional load, torsion stress. This is the axial load and bending stress. So these are in this type of problem, this resultant stress step is involved only when we have combined loading. That means both the axial and bending condition. Here, if you exclude, even though if you exclude the torsional load, there will be a axial load and bending load, right? So it's a combined loading case. So only then that type of case will be finding the resultant stress at the top and bottom, or A and B. Okay, that is what they asked to find, because these are the 2 points where maximum stresses are formed, right? The A and B. So how do you find resultant stress at the A is sigma D plus sigma B, and at B is sigma D minus sigma B. I assume the axial stress at I taken the letter as D. You can take any letter. I am calling the axial stress as sigma D. So at the point A, what really happens is 25 kilonewton is it's a uniform. This axial load is uniform, so it will be same. If you take any cross section, it will be there, and it is uniform. Load is 25 kilonewton act uniformly. So at point A, this 25 kilonewton, sorry, the stress due to this 25 kilonewton is there. Sigma D plus sigma B. Why plus sigma B? Why is a positive sign? Just imagine what really happens when this 5 kilonewton force apply. This thing will sag, right? It will be like, it would bend like this, right? It would bend like this. This bar would bend something like this, right? So the top bottom here is tension. Okay, at this point there will be tension, and the bottom portion will be having a region of compression. So basic convention, whenever there is tension, will be adding, and the compression is negative, right? So the top part stress, if you take the resultant of the top part, the axial load plus due to bending load, which are here the top portion due to the bending load will be having tension. So the stress due to that is taken added to the axial load. Okay, that's why the positive sign between the stresses. But in the case of B, same way, here is the why is negative is because this B, the stress due to the bending load is compression at the bottom portion. Compression we have to take negative. So take the difference. So you get the minus 97.26 megapascal. This is the second step to find the resultant stress at A and B. And these steps are mostly used when we have a combined load condition. Next, the what they simply ask to find the maximum stress at the point A and B. A and B. So these cases we have to find the principal stresses. Okay, these are that type of question. So principal stress at the A. Okay, let's just consider the top portion alone. Principal stress at A, you just find out the resultant stress at the A as like 140.94 megapascal. So this is a principal stress equation. Basically, at single portion there will be maximum principal stress and minimum principal stress. Various term in it is this equation for principal stress are sigma x, sigma y, and tau xy. So this top portion, the x direction, the net load or stress in the x direction will be the resultant stress at A. Okay, there will not be any resultant stress in the y direction. So this type of question, when cantilever being having an bending load, okay, so sigma x is equal to sigma a. This resultant stress value will be sigma s, and there will not be any stress to y direction. So sigma y is 0, and tau xy. Basically, there won't be some effect of shear stress. So tau xy will be 34.36 megapascal. So this is the way to solve this type of problem. Just keep in mind, just follow this pattern. Just don't need to think too much. So now we have all the terms to substitute into this equation, right? So the principal stress, there's maximum principal stress and minimum principal stress. The only difference between the maximum principal stress equation and the minimum principal stress is the difference in sign down here. Okay, all other equation, and I mean like all the terms are same. So I'm calling the maximum to be 1a, and the minimum to be like uh, 2a. Okay, that's your choice. You can call it an n term. So maximum principal stress you can find at the point A. We have all the term now. So substitution will get us maximum principal stress as this value. So next is to find the minimum principal stress at point A. I already told the difference between maximum minimum is negative sign. So all other term is same. So the minimum principal stress at A will be minus 10 megapascal. You can also find the shear stress at that A part. Okay, maximum shear stress developed at the A region. That's 67.47 megapascal. They haven't asked in the question to find the maximum shear stress. Okay, but when they ask the stress, we have to find all the terms like maximum principal stress, minimum principal stress, shear stress. Okay, so this is all the stresses are related to at the point A, the top part of the shaft. When considering in the B, we know the resultant stress at B, which is found at as minus 97.26 megapascal, and it will be the sigma is the stress in the x direction, and there will not be any stress in the y direction, and there will be like shear stress due to and the x and y combined due to the torsional load that will be 35.36 megapascal. Okay, in this type of problem, the thing is that resultant stress will be taken as sigma x in the case of both the top region and bottom region. But the stress in the y direction sigma will not be there. The value will be 0. And tau x y is will be there. It is given. I mean, the torsion load is there. So same way you can find like the maximum principal stress and minimum principal stress is like region A. Here I haven't written the original equation because I already written previous part. So there will not be in white term. So it will be simply sigma x by 2. So all other is a simple substitution. To find the minimum principal stress, the only difference is a negative sign here. So we got the max value of both the maximum principal stress and the minimum principal stress. Similarly, we can find the maximum shear stress at B. Okay, same equation, this same equation. So this is a way to solve this type of problem. When they ask to find the stress at A and B, we have to find all the stress, minimum principal stress, maximum principal stress, maximum shear stress at separately at this both the region in this combined loading condition. Okay, this is a way to solve this type of problem.